This is problem 7.8, and we are calculating the internal forces in this beam. And the internal forces will be the actual force, the shear force, and the moment. First step in calculating the internal forces is to calculate the external forces. In this case, we have a support at O that restricts displacements in Y and X. Therefore, we will have two reactions. And in C, we have a roller, which restricts only one reaction. So step one is external reactions. To do that, I will draw the free body diagram of the whole beam. So at 3 meters from C, we have a concentrated load, and at 2 meters of O, we have this is 9 meters, right? So this is 6 in total. So this is, if this is 6 and this is 2, this has to be 4, right? Okay, so, and then we have a concentrated load right here, which is 1,000, and then we have, this is a distributed load, constant, therefore 150 times 2 is 300, and it's located at 1 from O, and I said it's 300. And it's located at 1, right? This is 1. Okay, those are the active forces. Now I'm going to draw the reactive forces, right? We said that at O we have two restrictions, motion in X and motion in Y. And in C we said that we have only restrictions in Y, therefore we have only CY. From here, now that we have our free body diagram of the whole beam, we will apply the equations of equilibrium. We see that if X equals to 0 leads that the force O is equals to 0. And actually, since I don't have any other forces in the actual direction, I can say that the internal forces in the actual directions will be equals to 0 all along the beam. Then I will take moments at C or at O, and then I have 1 meter. This is a negative, right? Because I will place my hand here at O, the distance, and I curl my fingers towards the force. This is negative 300. Then I have again 6 times 1,000 is negative 6,000. And then I have 9 times CY. And that's equals to 0. That means that CY is equals to 700 newtons. Adding forces in Y, I have OY plus CY minus 1,300 equals to 0, and that allows me to find now OY. And OY is equals to 600 newtons. Okay, now that we found the external reactions, we will be able to find the internal reaction. We could substitute our external support by the forces that we found. So here we have a force that is OY, which is 600 newtons, and here we have a force that is CY, that is 700 newtons. And as I say, we don't have any force in X because OX is equals to 0. First of all, we have to figure out how many sections do we want to divide this beam into to find the internal reaction. So we will cut the beam as many times as we have events. What is an event? It will be distributed forces, concentrated forces, or a concentrated moment. In this case, we see that we have a distributed force, and then we don't have any distributed force, and then we have a concentrated force, and then we don't have any load. So I will divide my beam in 3 sections. I will call this section 1, I will call this section 2, and I will call this section 3. And I will do the free body diagram of each of these sections. So this is step 2. And I will analyze of each section. I will do the free body diagram of section 1. And then I will do the free body diagram of this little piece over here. I will call this X. So why X? Because that section will be valid from 0 to 2. And X will be a variable that can take values from 0 to 2. Then I do my free body diagram of that section, right? And I have this force over here that I know that is 600 newtons. And I have a distributed load, right? That distributed load is a constant load, but what I will do is make a concentrated load an equivalent only for that section. Since this is 150, I will multiply by X, so it will be the height by the base, so it will be 150 X. And I don't have any other force, I only have the internal force. As I say, I'm not going to do the analysis of the normal force, because we got that the normal force for the reactions is 0, therefore all the internal forces will be 0. So I have the shear force and I have the moment. Now I apply equations of equilibrium to this section 1, and I add forces in Y, and I got that 600 minus 150x minus V is equals to 0. Therefore, V will be equals to 600 minus 150x. And this is my units of this force is equals to N. And then I will take moment. I can take moment in this point that I can call A, not to call it O, which is my point where I will make the cut. So I will take moment at this point A, and that will be equals to negative 600x, right? Because this distance over here, I said that this distance over here is x. And then I have 150 positive x. And what is the distance from A to 150? Is x half. So this distance over here is x half. So I will multiply that by x half. And then I have plus the moment is equals to 0. Therefore, I can write that my moment will be equals to positive, right? Because it goes to the other side, 600x minus, and I can, this is x times x, give me x squared. And this will give me 75x squared. And the units for the moment are Newton meters. Okay, so as you see, I can start drawing my diagrams. And as you see, I have my force V here, and I have my moment. I have to just make sure that I will have enough space to draw everything, right? Okay, so as I said too, I will divide this in 3 sections. So I'm going to divide it like that. This will be my first section. This will be my second section. So I already have the equations for the first section, which is this one right here. And I see if I evaluate that at x equals 0, I get that V is equals to 600. And if I evaluate x equals 2, I get that V is equals to 300. So I go from 600 to 300. And how do I get from 600 to 300? With a straight line with a negative slope. So this is a straight line with a negative slope. So if I write the equation for that, is 600 minus 150x. And for the moment, I have, if I evaluate at x, I get equals to 0, right? And if I evaluate in x equals 2, I get 600 times 2 and 75 times 4, negative, right? So, and I get this value, I have it right here, is 900. So this is 900. And how do I get from 0 to 900? So what I did was, I will do it right here. For x equals 0, I get the moment is equals to 0. And for x equals 2, the moment is equals to 900. How do I go from 0 to 900? I go with a quadratic curve, negative concave down. So I have right here my curve, right? This is equals to 600x minus 75x squared. Okay, so we did the analysis of section 1. Let's do the analysis of section, free body diagram of section 2. So I will draw now my x. I have explained that in several other videos. You can name x starting from the beginning. Let me draw this correctly. This 2 is still over here. So you can name x from the beginning of the beam, or you can name x when the section is become valid, right? So I like to do that. For my second section, I will name x from here. So I will have 2 plus x. Then I have 2 meters, and then I have x. And then, as you see, I am beyond the distributed force. So I already can put a concentrated force at 1. And this is 300. So it's the same 300 that I have over here. Okay, and I don't have anything else, so I can draw my moment, my shear force and my bending moment. And I will do my equations of equilibrium now for this. And I will add forces in y, and I have, oh sorry, I forgot, of course, I cannot forget the 600. So I have 600 minus 300, now I don't have an x because I am beyond my distributed force, minus v is equals to 0. So what I see here is that v remains to be 300 for the whole section. So if I draw that, I will draw something like that. So it's a constant, and I start and end my section with the same magnitude of the shear force. And then I add moments. I will add moment. I will call this point A again. And I will take moments at A, which is a moving point, right? I just call it A. You can call it different names if you want to. I'm just moving that point A along anytime that I've changed sections. And here I have, what do I have? I have the 600, the distance will be x plus 2. And this moment is negative. And then I have this moment right here will be x plus 1. And this moment will be 300. And then I have plus m equals 0. So if I solve for m, I have x 600x, and here I have 300x. This is negative, this is positive. So finally I have, and as you see, I have 600 times 2 and 300 times 1. 300x, 1200 minus 300 give me plus 900. And that's newtons meters. Okay, so we were able to find the expression for the moment for the second part. And as you see, this becomes a line. So if I evaluate for x equals 0, I have m equal 900, and I evaluate for x equals. This segment is 4 meters, so I have to evaluate in 4 meters, and I get the value of 2100. So I go from 900 to 2100 Newton meters. And how do I get from 900 to 2100? I go with a straight line with a positive slope. So I go with a straight line with a positive slope. And this here will be equals to 300 x plus 900. Okay, so, and I will use this space over here to draw the free body diagram of the third section. As you see, the third section, if I draw it from here, is a little bit long, but I will do it so that we get clear that we can do either draw this section or this section. I will draw first this free body diagram just to continue with the process, and I will do the analogy, what happens if you draw the right side. So let's start now our x for the third section, measuring from here. So this is the first x, this is the second x, and the third x. So I will do the analysis of section 3 over here. And as I said, I will draw this whole free body diagram. At 1, I have a concentrated load of 300. Then now I am beyond this 1000, so therefore I have to draw my 1000. And this 1000 is located at 6 meters. And then I have, this is my x, and I have now the internal forces, right? The internal forces are always the same, V and M. Okay, now I have my free body diagram and I apply my equations of equilibrium as usual. So finally, of course, I have to multiply all that and do the algebra and solve for M. And the equation that you get for M is negative 700 x plus 2100. Please do the math. It's very easy, right? This is algebraic math. And we get this expression over here and this expression over here. So, as we see, if we draw our system, here we have that for the section 3, this has a value of negative 700. So this is positive, and this is negative. And here, if we evaluate for x equals 0, so we are right here, we got that m is equals to 2100, and for x equals 3, we get 700 times 3, which gives me 2100, so m is equals to 0. Sorry that my handwriting is not so good at the end of the screen. Let me do it again. Equals 0. Perfect. So I go from 2100 to 0. How do I get from here to there? With a straight line with a slope of negative 700. So this is negative 700 x plus 2100. Okay, so very important that here we have some discontinuities. I have said many times that anytime we have a discontinuity, we have to check that those discontinuities have the same magnitude as concentrated loads in the case of a shear diagram. So for example, here we have to start in 0, and here we have a discontinuity, and this discontinuity has the same magnitude as the 600. Here too, I go from 300 to negative 700, right? So therefore I have a discontinuity. And here I go from 700 with this concentrated load, I go to 0. So my graph starts at 0 and end at 0. That's one way to check that my diagrams are correct. Then I have the moment diagram that start at 0 and end up at 0, and it's all positive. What does it mean that it's positive? Our convention sign means that if we get a positive, that whole beam, it will be deflected concave up. So this is our diagram, and as you saw in the theory, the bending moment diagram is related to the shear moment diagram, and the shear moment diagram is related to the distributed loads. If we have a constant distributed load that goes downwards, we will have a linear shear diagram, and we will have a quadratic bending moment diagram. If we do not have any distributive load, we have constant shear and linear moment. If here we have, I already talked about the concentrated loads, and here again, we do not have any distributed load, therefore my shear diagram is constant, and I have since this is negative, I have a linear moment, and so my slope here is the same as my shear, and my slope here is the same as my shear. As I said, this is the solution of this problem. This diagram was a little bit long. You could also, so I like to make sure that you understand that this is another approach, and you don't need to do it if you did already this one. Approach for last section, which is section 3. I could do the free body diagram of this little piece over here, and I will write my external force, which is 700, and I can measure my x from here in this direction, x, and then I will have my internal forces, and here you have my internal force. If I apply my equations of equilibrium to this little piece, I have that adding forces in y, I have 700 plus v is equals to 0. So it gives me the same negative 700, you see? And then apply moment at this point A. I have 700 x minus, right, equals 0. So A, and I have a positive. So in this case, you see that m becomes 700x. But be careful, because x now starts 0 here and 3 over there. And it will be a straight line going up and end up in 2100. So if you want to use this approach, that's good too. This is much shorter, but you have to be careful that the x will be starting at the other end. You see that here the x starts from here to there. In this case, x starts from here to there. But you will get the same graph. So use the approach you feel more comfortable with, either always drawing the left side diagram or diagram, but you have to be conscious and you have to understand the concepts. And as you see, I draw the internal forces in the opposite direction as if I draw the diagram in the left side.